Welcome back. In the previous video I said we'd be implementing rendering to textures like high resolution screenshots basically. But I actually had a look at that off camera and it's a little bit annoying, so I just went ahead and implemented it. It's not so interesting. But yeah, so let's get started here. What I want to do in this video is basically try to recreate some of these interesting shaders that you can find on ShaderToy. And I think we should start with this one. So I'm actually going to copy this stuff. And then we'll call it, what will we call it? It's not called anything, so we'll just call it like, it says add credits to this guy, so Guanabara shader, we'll call it that. And let's see if we can get a shader. Here we have a shader. And let's go here and actually open up the thing. Okay, and here's the reference code. So we want to try to understand that. In the end, we have the frag color, which is our out color, and it's given by C divided by L, and T is something, I don't know what is. T is the time and R is the resolution. All right, so basically it would be something like, well, let's define a C and L, maybe they are 0 to begin with. It would be something like this. And actually let's just explicitly define them. And this one maybe we'll define it to be 1 to begin with. So we have that. It should give us a black screen. There we go. All right, there's also a set. So let's define a set. They are actually equal to the time. They are not equal to 0 or 1. And they are floats, which is nothing I didn't really notice. So they are floats. Then we have a for loop. And this thing we don't need anymore. All right. Then there's some kind of for loop. Plus, and then we construct this thing. So it's the coordinate divided by the resolution. So this is something that will go from 0 to 1, I'm pretty sure. So that means we should probably define our own P to be the position plus 1 divided by 2. Actually, like, this is so common that maybe we should have it part of the standard shader, but whatever. And this is also UV, it's the same thing. Great. So what happens here in the shader? It says UV equals P for some reason. And then we have P minus a half. So we shift everything. So now the coordinates go from minus a half to a half. So actually we can just do plus divided by 2 and not have this. And then we have R, which is the resolution. So this is kind of like the aspect ratio. We always have 1, so actually we don't need that. Then we add something here. L is the length of P. UV is P divided by L times sine of Z plus 1. So I'm just going to write it out. And then we're going to try to understand it. And see I, so we're setting all the components. Thing. And the UV, take the modulus, subtract the half. Okay. Interesting. So does that actually give us anything? No, because it doesn't compile. And we have one too many here. Okay. So it's not too different. It's not too different. It's a little bit different. This is more circular. Ours is definitely not circular. So I wonder why that is. I wonder why that is. Let's see. Set these guys we didn't need. U equals P. This one probably we should actually have that in here. So we reset it all the each iteration. Okay, actually did not matter. Which I guess makes sense also because okay, are we possibly missing something? P divided by L. We are actually missing. There we go, I think. Okay. Now it's more circular. All right. It's not fully circular, so maybe have some other typo. Okay, let's go through this thing we don't need. We're actually not using that. So C doesn't matter what it is. There's a time less than 3 plus 0.07. Just out of interest, what happens if I change this? Okay, colors change a lot. The length of P and what happens if we do this? Just scales it out a bit. Sine. And we have these two. Why do we have that? Nodes. Okay, let's look at the shader again. Maybe it is correct. Let's look at them side by side. Actually, why don't we do that? That's not what I wanted. There's no way to get rid of this. So the view is a little bit different. Maybe we actually try to zoom out a lot. How about this? It's a little bit too much, but whatever. So we get these like rays of like 4 pairs of 2. Which is, don't see it necessarily over there on the left. But at least it's not completely wrong. Maybe it's right. Maybe it's just difficult to see. All right. Could it be, what if we do +1? What happens then? No, we just get this section, which also looks cool. But let's try to understand what's happening. We set each component to this thing. Okay. And we add a little bit. So this is all the color channels. And the kind, so the color channels change a little bit, but the overall brightness is defined here by it's kind of like dependent on the radius a little bit. Yeah, definitely, because we also divide by L. So the point, the distance from the center determines it. And we have to do something like this. Okay. Interesting. So basically we have this, what happens if we just get rid of all the time dependence? Maybe that will show us something. Yes. So we have this kind of pattern that oscillates as a function of the radius because it depends on L. And there's also this thing. So we have kind of like a, if we don't do that, if we do like a vec3, 1, sorry, vec2, 1, we get this, which doesn't look good. So there's also here, we have the coordinates that somehow make an appearance. And then we have this is just some modulation with time. And this is some modulation both with distance and with time, and also a little bit different for each color channel. And then this thing, I wonder what would happen if we just did like times mod UV1. And that did not work because it's a vector, so let's take the length. It looks weird. Mine's a half. So yeah. Guess that's to be expected. Because UV is kind of like the position. Going to 0 as we go further away. Yeah. What if we just set this CI to like the length UV? That's very bright. UVX, probably also extremely bright. And the absolute value, because it's going to be negative, of course. Yeah. We divide, it's also kind of crazy looking. Okay, let's just stay with this one. And yeah, it's difficult to, why do we get this radial dependence? Can we see if we can understand that? So none of this except the UV, of course, depends on like the angle. This depends on the angle. If we do something like that, that also looks cool, honestly. YX probably doesn't do anything interesting. And XX. Did I already do that? How about YY? Yeah, so it's actually only through this P that it has a dependence on the angle, I think. The Z is a float. L is a is also float. So it can only be the P that changes things. That's very interesting. All right, let's look at one of the other shaders. So let's start by creating that one. And I think this particle experiment. And we're gonna call it, we're gonna Run a new project, and we'll say projects, and we'll call it this name, which I don't know how to pronounce, shader. All right, so we got the shader, and we'll go here, get the shader code, and look at this here, reference code. That's a lot of code. That is a lot of code. So let's do a little bit of copy pasting. We have t, which we just call time plus 1/2 plus 5, sorry. Then we have set. We have some particle count. We have a start color. We have an end color. We have some radii. We have, I'm gonna keep the S, but our resolutions probably just, we can, I'm actually not going to keep it. So this goes from 0 to 1. So I think this is basically our position. Because frag coordinates goes from 0 to 1, then we multiply by 2, it's 0 to 2, then we subtract the resolution, and then we divide by this to scale it down. So yeah, that should be that. We don't have a mouse. We don't have mouse input, so we're not gonna think about that. We have some colors, some PM, which I don't know what it should mean, and some floating point. Great. I think we're getting to the most interesting part now. Which is this. Why they write it like it's kind of crazy notation, I don't get it. Sure. Okay, so that is some kind of thing that varies in time. And we have that. Then we have a number of iterations, which is okay. So this is, we'll put each iteration of the loop will produce a particle, and distance, radius. So can we try to figure out what the position of the particle is? It's probably this x and y. We have, what's the duration again? Duration is 4. We have some kind of crazy number which I don't get. Then we have this kind of a distance, something like that. And there's some mix and stuff functions. So we probably need to find those as well. Maybe they're built in. This didn't complain. So say out color 4, color 1. So let's try that. So smooth step and clamp and okay, there's a lot of built-in functions I didn't realize. And it looks like this, which is not right. And why is that? Why is that? Because I copy pasted things. I did ignore some stuff. The S, for example, but the S doesn't factor in later. It was only maybe it's not right that we use the position. Where was it that we used that? It's here. Maybe it has to be from one. It was not that. So that's annoying. That is annoying. All right, is there something we're missing? Well, now we're getting just circles here as well. Is it really relying on the mouse a lot or something? Some mouse stuff. Did we break it? So it's really dependent on the time. So at some point it like starts to just be a circle. So what we need to do is say like, let's first of all place time with new time, and the new time is going to be the old time, but at most like 10. Let's try that. Yeah, so that looks more correct, right? That looks more like what was intended. Let's stop that one from running. Let's just admire it a little bit. Somehow it would be nice to actually see the time somewhere, but okay. Whatever. Oh, now we get a bunch of... So we have an A, which is giving us the angle of the particle, and it's kind of, you know, distributed evenly around. So what if we do like 2? So for fun, it's not, you cannot really see that. If we do this, then they're all sort of in the same direction. So this is like the angle of the particles. And yeah, this is kind of this trick I talked about in another video. If you have a function like f of y equals f of x, you can basically set the color to something like this, y minus f of x, and you might, I mean, I think what they are doing is basically something similar. So we have the p, distance right here. So what is this stuff? What is the end color? The end color, is that just the background? It doesn't look like it. It's not the background. And that's because it's because if this one is 0, then we just get the original color, which starts out as black. So basically what is the NB radius? There's so many things going on here. Okay, but basically they are saying something like this, and then what's V? What is V? V is basically the position. Okay, that's basically the position. So they are saying how far am I from this point that I decided that is a particle? So they're basically saying like the distance, let's write it like this, distance between screen coordinate and particle coordinate. And actually distance squared. That's what they're doing here. And then they have this mix. What is the sum being used for? Sum is some kind of normalization. Okay. That is interesting. What if we remove that? It looks like this. Great. Imagine if people actually gave meaningful names to these values instead of MB and MB radius and stuff. But okay, the basic principle is that you generate a lot of positions and then you give them some color. We can even, this is like basically the color. So the sum. Okay. I suppose we can do something like, length of P should be very simple. Thing that doesn't change too much. Maybe here divide a little bit. So that kind of gives a different expression. We do have a vector, and it's kind of like distance. It's hard to, we can say like px times py maybe. Then we get something like this, which is very interesting. And what if we just add a little bit? Then it becomes significantly more boring. Okay, what else can we think of? What else can we think of? What if we do plus? What if we do minus? What if we do times both of the apps? Kind of same. Yeah, it's hard to get around the need for using the distance. We could try like a different power. So something like, if we do the dot product, it's 2. So what if we try 4? They become more bright. We can try 1/2. Then it looks a little bit like this. But really, maybe if you were to try to develop this, what you do is something like, let's say we have a particle at 0, 0. And this thing up here, I didn't think about that, but that's kind of insane. We can call this P1 and this one P2. Let's get rid of those, and then we'll make those uniform float P1, P2, and we'll add some controls for that. So P1, and accidentally I took a screenshot. Because if you press P, then that's a bug. So we can change these values, and it's not really changing things a lot. So, but the D is kind of like, D is a radius. D is a radius. So if I set D equals 0, they should all be in the center. Yeah, D all in the center. So anyway, let's try to, we put a particle in the center, and then we have the distance radius, which is kind of like the distance from the, okay, so that's why they kind of fall off. If I do this, it should be as if they are further away, so that they should be much darker, or they should perhaps go to 0 faster. Nothing's really happening. We found P1 could not be found. It says, fine, let's just get rid of those, I guess. Anyway, so if we set the distance ratio, oh, we should set it to a very large number maybe. All right, so if we set this to a large number, okay, whatever, I don't get it. So we mix the start radius and the end radius, so it's like MB, I wish I knew what that stood for, but we have some like particle radius, so particle radius, and we set it to 1, why not? We don't have any better idea. And then we have kind of the let's call it delta position, right? So it's the position on the screen, which we for some bizarre reason called V, and that's the position of the particle. All right, then we have this stuff. We have MB, which is going to decide the color. Okay, it's the particle radius divided by the length of the delta position. That should mean that if we let's not call it MB, let's call it and why is it, yeah, it should be a float. So it's like the color strength for this particle, or something like that. So you see this delta position is kind of like how far away, the length of the delta position is how far away you are from the particle. So if we're super far away, this is close to 0. If we're very close, it's close to infinity. And then we have this thing, the color. So the particle color, it's 3. And it's kind of like a mix between, let's say, 0. Right, it's a mix between 0 and some kind of like particle, let's say base color, or maybe this thing is actually like we want that here, and the particle color, let's make it red for testing purposes, maybe like this. And then let's call it like position color, why not? So it's the particle color, and we use here the color strength. Okay, can get rid of all this now. Can get rid of that. This one I want to keep. So let's see if that works. Did not work at all. Great. Very great. And why is that? What if we? That's because we didn't actually use the right variable. Okay, so position color. Great. So now we have this particle, and we do have some like normalization, which I don't really understand. it's sort of like the sum of all the distances. Okay, whatever. But here we have a particle, and right now it's very red. Maybe we can make it a little bit like this. It was kind of interesting that, okay, it's because the middle is very bright. So color, this one, maybe we can clamp it from 0 to 1. Is that a thing we can do? All right, so that's a little bit more correct, I guess. Is that what we're doing here? There's no clamping. Actually looked a little bit more interesting without the clamp. How about we get rid of that? We have this thing. We can just decrease it a little bit. Okay, it doesn't really matter. If we make this number smaller, we should get a smaller particle. That's a very small particle. Maybe like that, which is actually kind of interesting. And then we can simply like make it move around, maybe like this. It should move around a little bit. And we can do things like that. So that's essentially what's happening here. The only thing is that the distance is kind of like this really weird function that depends on time. So I suppose we can do that too. We can say distance equals a weird function. And what is a weird function? Maybe it's hyperbolic sine times time of the time times 3, and maybe we like use the sine of that on that, and we multiply by 1, or we add 1 and multiply by 2 or something like that. And we have to use it as well. So we use it here, and that did nothing. So I wonder what d is. What if we just say d? So the hyperbolic sine, this thing, and we use the sine on that. If we decrease, at some point, okay, so something is super wrong. What if we do 0 here? That is great. So what if we do 1? Okay, let's do 1. That's the same as before. And I do wonder why. Let's do sine of time plus 1. Now it should do some more complicated movements. It's kind of tracing out this weird shape. Okay, but whatever. So what if we do again something like this fractional thing? It's probably not. Well, let's try. So fractional thing of like this. I don't know, whatever. That has some really crazy behavior. It looks like it's duplicating things. Maybe multiplying by 30 is not good. And probably like it's not very interesting. So what if we change it to time? Okay, whatever. Fractional thing of that. Now it's doing really weird things. And what if we do hyperbolic sine? Okay, it just like fucks off to somewhere. So maybe the problem is this number becomes too large, so we have to do a sine in here. So now we get this behavior. One thing is though, it doesn't like go out. So what we can do is, like, it doesn't go away, like out of the view. But we could do that just doing like plus time, then plus something like that, something like this, and really maybe like tangent hyperbolic time. All right. But we have this thing. It's a little bit boring the way the position is given. So here we have like, they're also evenly distributed. But we can like try to do something. Like if I knew more about hashing functions, that'd probably be interesting to use here. So time times time, like this. What does that do? That's a little bit too crazy. A little bit too crazy. What if we just do time times time? Too much. All right, that's like still weird. Okay, times 2 here. Anyway, you can play around with it, obviously. So what we could do is say something like I less than 10. Let's add 10 particles. And what would we do? Now we kind of need to add up the color. We need to add up the color for all the particles. So we need to pull this one out. Maybe initialize it to be 0. And then if we do this, we of course have the issue that it's only the last particle. And we also need to like do something here. So let's say like plus I, maybe this one's plus I times time, like that. All right. The time is a little bit fast. So what if we say kind of like time, replace it with scale time? And then we'll say flow scale time is like, please go half as fast. Okay, that's better. Right. So what we want to do is maybe not just the only difference is we don't mix with 0, we mix with the color, the previous value of the color. And then we get a bunch of particles like that. We have this really cool effect when they kind of meet, which I didn't expect, that it's kind of like blacks out for a moment. So that is super cool. Speed it up again. Speed it up a little bit more. And they kind of move in this weird random way, but like it clearly looks like there's some structure. And if we do, well, we did do that. What if we did like multiply by I here? Then we can get them to, it actually looks really cool. And we add a few more. So now we get very bright. Like it's a little bit too bright. What if we do this? Right. So the problem is somehow even far away points, they now get a lot of color. I wonder if that's some of the stuff here. Anyway, what if we do particle color? We say distance. So the MB radius depends on the distance to the center, and the MB radius also, the distance ratio also determines the color of the particle. So it will change with where it is located on the screen. Okay. Anyway, what if we decrease the color strength the further away we get? And we get something like this. Which is not what I want. This is not what I want, but we can try to work with it maybe. Now we just get the particles moving. Actually, I kind of like that there was a little bit of background. So let's try to change it back. Like, what if we do this? Oh, this. It's kind of interesting. So maybe if we're too far away, we change the color a little bit. So now we're starting to get into, so here we're going to say mix between this if we're really close to the particle, and if we're far away, let's try to make it just red. And the mixing thing is going to be something like here. Mix factor will be right now just the length of how far away we are, and the mix factor like that. Okay, so it quickly becomes red. Let's actually make it black, so it's a little bit better. Right. But what if we do like that? So these lengths should actually all be less than 1. So it means if I take a large power, it should become close to 0, which didn't happen. Or if I take a very small thing. Now we get this. And then if I mix in like a little bit of green, we get something like this. That's cool. Like they become this color, which maybe we can make it some kind of complementary color if I knew about color theory. All right, so what's actually happening? We're saying here, the further we are away, we're gonna be more towards this kind of bluish color, which further away we are from the particle, the more they will contribute with that. We could also lower the particle strength even more. Funny thing is that it creates these, they somehow become, yeah, because we need to, yeah, so when you increase this power, the small values, like the values close, will become much larger, and the values far away become much smaller. So it has this kind of behavior. Okay, that makes a lot of sense. I think we're gonna stop here for now, but this was fun, and I don't know if I'm going to do more videos on this project. I might play with it a little bit myself and maybe share some of the shares I come up with, but I don't think there's so much more interesting stuff that we can do right now. So until next time, I hope you had fun, and I will see you then.